Collisions can fall into two separate types of categories: elastic collisions and inelastic collisions. Regardless of which one we talk about, one thing is always true: momentum is always conserved. In other words, whatever momentum you have at the beginning, it's going to be equal to the momentum you have at the end. The difference between these two is that in an elastic collision, whatever kinetic energy you have at the beginning, it's going to be equal to the total kinetic energy you have at the end. That's an elastic collision. In an inelastic collision, these numbers don't match up. In other words, you'll end up losing some of that kinetic energy. An example of that is, for example, when you unfortunately get into an automobile accident, where initially the two vehicles are moving, so they had kinetic energy, and then at the end, they both become stationary. Often, what happens is that the kinetic energy is converted into some other form of energy, such as heat. And that's why cars often have these things called crumple zones. It's to convert all that kinetic energy into another form so that that energy is not dispersed into the passengers inside. So let's go through a few mathematical examples to clarify what's going on here. Okay, we've gone through this example last time, but let's go through it one more time. All right, this is an example where you have two separate objects, and when they bind together, they both share the same final velocity. So let's figure out what velocity these two objects share together. Here's some example numbers that we can crunch through, but we'll start off with our statement. As I mentioned, in all types of collisions, momentum's always conserved. So whatever momentum you have before is equal to the total momentum afterwards. All right, so we have object 1, we have object number 2, and at the end, the first statement would normally be m1 v1 apostrophe plus m2 v2 apostrophe. However, since they share the same final velocity, how about we just erase the 1 and 2 and in fact just call them both apostrophe, and then we can factor it out. So v apostrophe is equal to m1 plus m2 on the right hand side, and left hand side we can't change anything. What we can manipulate right now is that since in this example the larger object is stationary, this term we could just cross it off. In other words, we have something that's simplified like this. And since we're solving for v apostrophe is equal to m1 v1, since that was the only object that was moving initially, divided by m1 plus m2. Sub all the values in. Pull out your trusted calculator, and then you get to your answer. There's an example that's often used in high school, and it's with a device that's called a one-dimensional air track. And here it is. You'll notice that the two objects stick together. These are known as perfectly inelastic collisions. If you go through the effort of calculating out how much energy there is in the objects, for example, this guy here had an EK of 1/2 mv squared, and this guy here had an EK of 0 since it was stationary, you would have found out that the EK at the beginning, is equal to 3600 joules. And then afterwards, since they're combined together, you would have a calculation of EK is equal to 1/2 120 kilograms, because it's a combined mass, times their combined speed squared. If you crunch that through, you're going to get 1500 joules. So you could see that a lot of energy is lost over here. The energy lost is often known as the binding energy. Here's another example. Little guy versus big guy. However, big guy is a little bit slippery. So when little guy tries to tackle big guy, couldn't get a perfect grip on him, so he still flowed through, but you may have noticed that some of the momentum was passed on to the big guy. Alright, so initially the big guy was stationary, but afterwards the big guy was moving just by a slight bit. First guy was moving very quickly, then this little guy slowed down just by a slight bit. Okay, so let's go through the calculation. Again, in all types of collisions, momentum's always conserved. So the total momentum before is equal to the total momentum afterwards. m1v1 plus m2v2, where since v2 is 0, that term goes to 0, is equal to m1v1 apostrophe plus m2v2 apostrophe. Just as a reminder, that's why we use the apostrophe here. It just saves a lot of effort in describing the velocity afterwards. And yes, technically speaking, there should be arrows everywhere. However, that's why we like to state and assume that there's a direction that's deemed as positive so that we can drop all those shenanigans and just keep things nice and clean. Right? And from this point on, if you want to sub in the numbers first and calculate through, I suppose you could, but it's good practice to know how to rearrange. So let's go and do that. Let's bring this term over to the left-hand side. So we have m1v1 m1v1 subtract m1v1 apostrophe is equal to m2v2 apostrophe. So that v2 apostrophe, which is what we're looking for, is equal to m1v1 subtract m1v1 apostrophe. And I suppose if you wanted to, you could factor out m1. And you're going to divide it by m2. Go through all the crunching, and then you'll get the answer for v2 apostrophe. Once again, we can go through the calculations of kinetic energy. So we find out what the EK is of this example. It's still the same as before, since it's the same first object that's moving at 12 meters per second. That translates to 3,600 joules. And if we do the calculation of the total energy afterwards, and remember, it's the total energy, so EK apostrophe is equal to 1/2 m1v1 apostrophe squared plus the second object, since that's now moving, so m2v2 apostrophe squared. I've done the calculation earlier, and this drops down to 1836 joules. Alright, so this is another example of an inelastic collision. And here's a really interesting example of a collision. Let's say we have two of the most bounciest people in the world. Little guy tries to attack big guy, but then they bounce off each other, like so. By little guy. Okay, and we end up getting these specific numbers right over here. Alright, go ahead. Pause the video and try calculating out v2 apostrophe. Ready for the answer? Once again, momentum is always conserved. So the total momentum before is equal to total momentum afterwards. m1v1 plus m2v2 is equal to m1v1 apostrophe plus m2v2 apostrophe. m2v2 was stationary, so that goes to 0. That saves a bit of effort. And since we're solving for v2 apostrophe, we can just simply bring it over to the other side. So v2 apostrophe is equal to m1v1 plus m1v1, whoops, not plus, minus apostrophe, all divided by m2. We can go through all the number crunching, and we'll get 10 meters per second towards the right for the big guy. If you want to see animation again, here it is. Boop. Alright, we may not notice anything special right now, but the calculation is really interesting. Because when we try to find out the kinetic energy before the collision, which is equal to 3,600 joules, and we try to find out the kinetic energy afterwards, which again is equal to 1/2 m1v1 apostrophe squared plus 1/2 m2v2 apostrophe squared. Well, if you crunch the numbers through, you'll notice that you end up getting 3,600 joules. And that's what's so magical about this one. The total kinetic energy before is equal to the total kinetic energy afterwards. These type of collisions are called elastic collisions. And if the masses were matched up, you may get an interesting scenario like this. You've probably tried that with billiard balls before, all right? Where if the masses of the two balls were identical, once they collide, the first mass that was moving stops, and the second one moves at the same velocity as the first mass. No energy was lost. Okay, let's go through an application of conservation of momentum. So even though energy may not be conserved, momentum is always conserved. All right. So bullets, they typically move way too fast for us to measure. Back in the 1970s, high-speed cameras were very expensive, and we really couldn't deem the results as reliable. So if you really wanted to find out how fast something was moving, you would try to make it slow down. One way was to fire the bullets into water and see how far it travels and do some magical math to figure out how fast it was moving. But there's another way that's fairly guaranteed and reliable. What you'd do is you'd take a bullet and you'd fire it against a suspended object. Guaranteed and reliable. What you'd do is you'd take a bullet and you'd fire it against a suspended object on top of a string. The whole system will bind together in an inelastic collision, and then the masses combined will elevate to a certain height. Yes, it'll swing down, but you want to pay attention to the height that it reaches, and hoping that the object won't reach up to this point over here, because if you did, then you have to restart the experiment again with a longer piece of string. Alright, so you just want to set it up so that it will elevate to a height without the box accidentally hitting the ceiling. Okay, so let's go through this calculation. I'm just going to shift it to the top. Alright, so they're trying to figure out how fast is this bullet traveling. You've already found out the mass of this, which is at 5.5 grams. You know the mass of the larger object. The length of the string, as I said, it doesn't really matter. It doesn't have to be too short. It just needs this whole system to just elevate to a certain height and make sure you're able to measure the height that's able to elevate at. Alternatively, you could measure the angle as well. Alright, however, with angle measurements, we're only certain with angle measurements usually to, only about 2 significant figures. Height, if you're careful enough, you should be able to get it to 3 significant figures. So that's the benefit of measuring the change in height. Alright, so at the end, we only see the end results. In other words, when they bind together, we find out what the final change in height is. So we have to do a bit of reverse engineering towards finding out what the initial speed of the bullet was. Okay, so we're going to start off with conservation of energy, because what happened here was that combined together, they had pure kinetic energy. At the top, it's all converted into potential energy. Effectively, you have an equation that looks like this: 1/2 mv plus mg delta h as combined objects is equal to 1/2 mv squared plus mg delta h final initial. So initially it was at its lowest height, so this term goes to 0, and at the end it stops, so this term goes to 0. What this tells us is that 1/2 mvi is equal to mg delta hf. And hey, look, we didn't really care too much about the mass because masses were on all the terms. So this formula really simplifies down to vi is equal to the root of g delta hf. So as long as we know what the height is, we can find out what the initial speed was of the two objects combined. And let's go through that. Oh, there's a 2. I'm glad this was animated out. Alright, so you sub everything in, crunch it through, and then you'll get the combined speed of both the bullet and the mass. Alright, so this is the combined fused mass. Effectively, this is your v apostrophe of the two. Okay, now we're going to move on to conservation of momentum. Alright, because again, in that inelastic collision, when the bullet fused into the mass, a lot of energy was lost. So we can't really, we could figure out the energy that was lost, but it's of no need for us. Instead, we just know that they share the same speed once they fuse together. Alright, so since momentum is always conserved, so total momentum before is equal to total momentum afterwards, we can have this nice formula now. m1v1 plus m2v2 is equal to v apostrophe m1 plus m2. Right, as they do share the same velocity afterwards. Again, the large mass was stationary before the collision, so that term goes to 0. So this simplifies things quite a bit, and all we're trying to solve for is v1. Alright, so now we can find out the initial speed of the bullet before the collision. That's equal to v apostrophe m1 plus m2, all divided by v1. Okay, now let's just sub all the values in, go through all the number crunching, and then you'll get to your answer of about 500 meters per second. Hopefully you know how to get to that point. Just sub everything in and crunch everything through. Your exercise now is to go through these questions here. Best of luck. Catch you in the next episode.